Hello everyone. Today we will be discussing the internal two solutions of numerical analysis and design. So let's start. My name is Siddharth Gupta, roll number IT2K2482. Enrollment number is DE2402061. So let's start with the question number one of our internal two solutions of NAD. The first question is to estimate the population in years 1925, 1975, and 1984 based on the census data. So here we have been given two tables, years and population, and we need to estimate the population in the years 1925, 1975, and 1984. So here we can already see the years are equidistant with a step size of 10. So we can see as the years are in equidistance. So we would apply Newton's forward interpolation or backward interpolation. So as we see, first we will form a forward difference table. So here first we will form the forward difference table. So as we already know that a forward difference operator delta, it is f of x plus h minus f of x. So for this, it will be for the first forward difference, it will be 42 minus 35 7, 58 minus 42 16, 84 minus 58 26, 120 minus 84 36, 165 minus 120 45, 220 minus 165 55. Then we will form the second forward difference, that will be 16 minus 7 9, 26 minus 16 10, 36 minus 26 10, 45 minus 36 9, 55 minus 45 10. Then we will form the third forward difference, that will be 10 minus 9 1, 10 minus 10 0, 9 minus 10 minus 1, 10 minus 9 1. After forming the third forward difference, we will form the fourth forward difference, that will be 0 minus 1 minus 1, minus 1 minus 0 minus 1, 1 minus 1 2. Then we will solve the fifth forward difference, that will be minus 1 minus 1, that is plus 1 0. 2 minus 1, that will be 2 plus 1 is equal to 3. And then the sixth forward difference will be 3 minus 0, that will be 3. So here we have formed the forward difference table based on the forward difference operator, that is f of x plus h minus f of x. Now, for calculating the population in the year 1925, we already see that 1925 is near the beginning of the table. So here we will use Newton's forward difference interpolation. So as 1925 lies here somewhere around 1925 and 1931, so we will use forward difference interpolation for finding the value of 1925. Now you already know that the formula for forward difference interpolation is y y of x is equal to y of 0 plus u delta y of 0 plus u into u minus 1 by 2 factorial delta square y of 0 plus u into u minus 1 into u minus 2 by 3 factorial delta cube y of 0 plus so on. So first we will find the value of u. So u is x minus a by h, where h is the step size, that is equals to 10. We have already discussed. A is the starting value, that is here 1921, and x is the year that for which the population is near to be found. So x is 1925. So we will put the values here, and then u will come out. Now we will put all the values in this formula. So for finding y of x, that is x is 1925. The first y0 is 35. This is y0, the starting value, the first population of the year 1921. Plus u is 0.4. Delta of y0 is the first forward difference, that is 7. Plus 0.4 into 0.4 minus 1 by 2 factorial 2. Delta square y0 is the second forward difference, 9. Then similarly 0.4 minus 1 is minus 0.6, 0.4 minus 3 is minus 1.6, divided by 3 factorial is 6, into delta cube is 1. So we'll put 1. Now after solving this, we will get the value of the y of 91925, that will be equal to 36.8256. So here we could conclude that the estimated population in the year 1925 is somewhere around 36.83. We have rounded it off to 36.83 thousand. So by this way, we can find the population in the year 1925 using Newton's forward interpolation. Now the second part is to find the population in the year 1975. So for finding the population in the already know that 1975 is near the end of the table. You can clearly see that 1975 is somewhere around this, that is the end of the table. So here we will use Newton's backward interpolation. So we will apply Newton's backward difference formula, that is y of n plus v or u, you can take anything, v V nabla. It is nabla, backward difference operator, y of n plus v into v plus 1 by 2 factorial nabla square y of n plus v into v plus 1 into v plus 2 by 3 factorial nabla cube y of n and so on. So here we will put the value of v. V is x minus xn by h, where h already the step size is 10. Xn is the last value, that is 1981, and x is the value we already know that for the which population is need to be found. So we'll put these values in the formula. Y of n is 220. Y of n is last value. Y of n is 220. Then delta y nabla y0 is 55. Nabla y square is 10. Nabla y cube is 1. Nabla raised to 4y is 2. Nabla raised to 5y is 3. Nabla raised to 6y is 3. So like this, we will put the values in this table. We already know the value of V. I already told about the value of nabla yn, nabla square yn, nabla cube yn. We will put all these values and we will find the population in the year 1975, and that will be 185.6768. So here the estimated population in the year is this around 185.66. We have rounded off it. So this is the second part where we have solved the population in the year 1975 using Newton's backward interpolation. So now we will solve the third part of the question, that is to find the population using Newton's to find the population in the year 1984. Now we could use either forward difference interpolation or backward difference interpolation to find the population in the year 1984. So here we will be using Newton's backward difference formula. So similarly, as we have did in for the year 1975, we will find the value of V by x minus xn by h is 10, xn is 1981, and x is 1984, for which we have to find a value. It will come on 0.3. We will put in the formula, same formula as we used here. We will put the values in this formula, and we will find that the y of population at 1984 is somewhere around 238.5607. So population, we could write the conclude our answer that estimated population in 1984 is around 238.56 thousand. So here we have solved the first question where we were needed to be found the population in the year 1925, 1975, and 1984. So for 1925, we use forward difference interpolation and find out the answer. For 1975, we use backward difference interpolation, and 1975 lied at the end of the table. And for 1984, we could use any forward or backward, but here we have used backward interpolation, and we have find that the value of 1984 population at 1984 is this. So here we have done the first question. Now we will be coming forward to the second question. Second question has two parts. The first part was to find the interpolated value for f 2.5 and 3.5, and the second part is to generalize the Lagrange for 2D quadratic interpolation. So solving the first part, we have been given a grid where we have to find the interpolated value at f of 2.5, 3.5. It is a question of Newton's 2D interpolation. So here, as we all know that x is lying somewhere around 2 to 3, as 2.5 lies between 2 to 3, and 3.5 lies between 3 to 4. So y lies around 3 to 4. So first we will calculate the grid points near these values. So grid point of f of 2, 3 is 51, f of 3, 3 is 61, f of 2, 4 is 29, f of 3, 4 is 49. These grid points are already given in the question. So for the step 1, we will interpolate linearly along x is equal to 2.5. So for f of 2.5, 3, it will be 2, 3 plus 3, 3. For 2.5 lies between 2 to 3. So it will be 2, 3 plus f of 3, 3 divided by 2. So answer will come around 56. For 4, it will be 2.5, 4. For it will be 2, 4 plus again that 3, 4 divided by 2. That will come around 39. Now we will interpolate linearly along y-axis. So for y is equal to 3.5, f of 2.5, 3.5 will come somewhere around f of 2.5, 3 plus f of 2.5, 4, as 3.5 lies between 3 and 4. So f of 2.5, 3 plus f of 2.5, 4 divided by 2, it will come around 47.5. So we have already found the value. So the first part is solved here, that we needed to find the value at 2.5, 3.5. So the value at 2.5, 3.5 will be the sum of f of 2.5 comma 3 plus f of 2.4. We have found the f of value of f of 2.5 comma 3 and f of 2.5 comma 4 by interpolating at x is equal, by interpolating linearly on x equal 5. It comes this. When we add up these and divide by 2, we get the value at f of 2.5 comma 3, that is 47.5. We have solved the first part of the question where we need to interpolate and find the value of f of 2.5 comma 3.5. Now we will move on to the second part of the question, that is to generalize the Lagrange for 2D quadratic interpolation. So to perform quadratic interpolation of a function of two variables, we'll extend the 1D Lagrange formula using tensor product. So it is saying that if we need to find the formula for 2D Lagrange, so we will extend the 1D Lagrange formula using tensor products. So assuming that we select 3 points in x, example x0, x1, x2, and 3 points in y, assuming y0, y1, y2, the 2D Lagrange formula will comes out to be sigma I is equal to 0 to 2 into sigma j is equal to 0 to 2 L of x comma ix into L of y comma jy into f of xi comma yj. So this is a 2D Lagrange formula that comes after extending the 1D Lagrange formula using tensor products. Then where Lx of Ix and Ly of Jy, these two parts are standard 1D quadratic Lagrange's basis formula. This uses 9 data points to form a quadratic surface. So here we have generalized the equation for 2D quadratic equation for 2D quadratic interpolation by extending the 1D Lagrange formula using tensor products. So here we have solved this question 2 first part for finding a value of f of 2.5 comma 3.5, and also we have generalized the Lagrange equation for 2D interpolation. Now we will move on to the third question, that is the numerical integration using Simpsons. So here we have been given a table that has an uneven step size. So we will split the table into two parts. We have been given a table like this where x is minus 0.6, minus 0.5, minus 0.4, minus 0.3, minus 0.2, minus 0.1, and after 0.0 it was given 0, 1, 2, 3. So we can see the step size here is around 0.1 and the step size here is around 1. So this table was given combined in the question. So what we will do, we will split the tables in two parts. We will split this table into two parts based on the step. So the first part will contain x from 0. Minus 0.6 to 0, from minus 0.6 to 0. This will be the part 1, and the part 2 will be from 0, 1 to 3. So we will break the table on the basis of step size. For part 1, h is 0.1. There are 7 points. N is equal to 6. So as n is even, so we will use Simpson 1 by 3 rule. For part 2, x is equal to 0 to h is 1. We already see h is 1, h is 1. And also there are 4 points, that are 3 intervals. So as n is equal to 3, so we will use Simpson's 3 by 8 rule. So for part 1, we will integrate. For part 2, we will integrate and we file the total integral. So integrating for part 1, the formula for Simpson 1 by 3 rule, you already know h by 3 is equal to y0 plus yn. Yn is here y6. So y0 plus y6 is 4 times like you can say odd pairs. So 4 times of y1, y3, y5 plus 2 times of even pairs like 2y2 plus y. So here we will put the values. H is already we know 0.1 by 3, y0 is 4, y6 is 2, y1 is 2, y3 is 2, y3 is 8, y5 is I guess minus 2. All these values are given in the question. By putting these values, we will find the first integral that will come around 1.766. Now similarly, we will integrate part 2 using Simpson's 3 by 8 rule. So I2 will be 3h by 8 into y0 plus y3 plus 3 times y1 plus y2. We will put the value of h is 1, y0 is 2, y3 is 8 plus 3 times of 3 plus 5. So we will put these values and we will find that out I2 will come around 12.75. So we integrated the first part using Simpson's 3 by 1 by 3 rule, and we integrated the second part using Simpson's 3 by 8 rule. And then we will add both the integrals and the total answer will come around 14.4833. So this is the final answer of the question number 3. So here we have concluded the question number 3, where we found the integration using composite Simpsons rule, where we use Simpsons 1 by 3 for the first part and Simpsons 3 by 8 for the second part. So now we will coming to the question number 4, where we have to integrate this using Gaussian Legendre, or you can say Gaussian quadrature formula. So here, as we can see, the limits are from minus 2 to 4. So firstly, we will transform this interval into minus 1 to 1 by this following formula that we have already learned in Gaussian quadrature. So what we will do, we will substitute the value of x. We will substitute the value of x this in this given equation. So what is the formula for x for converting this limit from minus 2 to 4 to minus 1 to 1? It is b minus a by t by 2 plus b plus a by 2. So the value of b and a is given here. We will put the values and x will come 3t plus 1. Now we will substitute this 3t plus 1 here. Also, what is dx here? Dx will be 3dt, as 3t will be 3 and 1 will be 0. So it will be 3dt. So now for converting this limits from minus 2 to 4 to minus 1 to 1, we will put the value of x to in function. So this integral will be converted into this. So why we are converting from minus 2 to 4 to minus 1 to 1, as we already know that Gaussian Legendre or Gaussian quadratic formula can only be applied on an interval from minus 1 to 1. So that's why we are converting the limits from minus 2 to 4 to minus 1 to 1. So here the x comes out to be 3t plus 1. Now we will integrate it. So the limits have been changed to minus 1 to 1. 3 comes here because of that dx part. So 3 dt, and the integral is 2 into 3t plus 1 cube minus 3 into 3t plus 1. So just substituting the value of x as 3t plus 1, and we have formed the equation. Now the equation has come out to be this. Now we will use n is equal to 4 and approximate and we will approximate I is equal to sigma is equal to 1 to 4 wi f of x. है ना? So we will the values of wi and xi are already given in the table in the question. So just we will put the values and we will integrate it. Now, why we are using n is equal to 4? We are using n is equal to 4 because the Gauss-Legendre quadrature with n point integrate polynomial up to degree 2n minus 1. Hence, here n is equal to 4, so it is exact for polynomials up to degree 7. Since our function is a cubic, the Gauss-Legendre polynomial will yield the exact analytical answer. Also, we will perform an analytical check where we will integrate this function normally using integration from minus 2 to 4, and the answer comes around 42. So the answer from this also comes around 42, and while integrating using Gaussian Legendre, our answer comes 42. So comparing both the analytical and Gaussian Legendre answer, we can say that the final answer is 42, as the answer is coming from both the parts as same. So here we have completed question number 4, where we have integrated this using Gaussian Legendre formula. Now we will move on to the question number 5, where we simply need to write the algorithm for Newton's forward difference. So let's start. First, we will read the n. N is the number of data points. You can clearly see n is the number of data points. Like how many data points are there? 1, 2, 3, 4, 5, 6, 7. So first we will read the number of data points. We have read the number of data points. Then we will read the array xn and y of nn. Y of nn. So what is y xn and y of nn? So these are the values. We will read this. We will read these arrays. This array and this array. We will read these arrays. So this is the second part. We will read these arrays. The next part we will read the value. We will read the value of xp, the value of x that we need to interpolate. Like here, we were given in a question like 1925, 1975, 90. So these are the values that we need to interpolate. So we will read these values that will be given by the user. So we will read these values. Next, we will construct the forward difference table. So for the formula for constructing the forward difference table, so we will form a for loop from j is equal to 1 to n minus 1. And secondly, we will form a for loop from I is equal to 0 to n minus 1 minus j. And the yij will be equal to yi plus 1 j minus 1 minus yij minus 1. So here, from this, we could calculate the forward difference table. This forward difference table can be calculated using this two for loop centers. Next, we will find the value of h, that will be x1 minus x0, and we will calculate the value of u. The u, you already know what is the u. The u is this value, this. So we need to calculate the value of u. So u here is, sorry, the u here is xp minus x of 0 by h. Xp minus x of 0 by h, what does it mean? The interpolated value minus the first value divided by h. That is the general we did in the question 1. Next, we will initialize sum with y of 0 comma 0, and the u, we will take u term as equals to 1. Now we will form a for loop from I is equal to 0 to n minus 1 to n minus 1, and we will say that u term is equal to u term minus u minus I minus 1 by I. So what is this u minus I minus 1? Here you can clearly see it is this part, u into u minus 1, u into u minus 1, u minus 2. And what is divided by I? That is 2, 1 factorial, 2 factorial, 3 factorial. So this is the that part only, u minus I minus 1 by I. So this is the u term. We will multiply each term again and again, because you know u minus 1, then again u minus 2, u minus 3, and we will keep on multiplying. So this, and I is the factorial part. Then we will add this in the sum and multiply it by y of 0 comma I. Why we are multiplying by y of 0 comma I? It is the you could say it is the that forward difference interpolated value. Forward difference, the value you find it from this. what the value of the forward difference table, we will multiply by this. So this will come out the sum. We will put the estimated value of the sum, and we will stop this. So it is a very simple algorithm where we read the number of data points, read the arrays, read the interpolated values, form the forward difference table, find the value of h and u, initialize sum of y00, u of term is equal to 1. Then for loop, we will time u of term is equal to u of term into this u part. Then sum is equal to this, and we'll print the sum and stop the result. So here we have completed fifth question for numerical analysis and design internal to solutions. We have completed all the four questions. So here we have completed numerical analysis and design internal to solutions. And thank you.